Hello, let's start chapter 16, which talks about acid-base equilibria. In this chapter, we are going to combine what we learned in chapters 14 and 15 about equilibrium in chapter 14 and acid bases in chapter 15. And we will talk about equilibrium in acids and bases. So, the very first thing we want to talk about is how to write the equilibrium equation for acids. When we say equilibrium, we mean weak acids and bases, right? Because for strong acids and bases, we do not have an equilibrium. They ionize 100%. So we talk about acids and bases, the weak acids and bases. And for acids, we first start with the acids. Well, for the weak acids, we write their equilibrium, or let's say we call it hydrolysis equation, with this equation. This is an acid, so it's going to donate its proton and it changes to an anion, then it will produce hydronium ion. Okay? And so Ka is written as, you remember we said only aqueous or gaseous compounds. We write them in the equilibrium constant. A times H3O divided by H2O is liquid. Its concentration remains constant, so we do not write it. You just write HA. That's how you write Ka. And I want you to keep this equation in mind, because sometimes you work with very large molecules or organic acids that you don't need to write down their complete formula. You just need to go with this. For example, it's acetic acid, HC2, H3O2. So what happens is that this acid, this acetic acid, gives its acidic proton C2H3O2 with a negative charge plus H3O. So if we don't know what is the formula of acetic acid, or if it's too long, we just substitute it with this. So keep it in mind, it becomes handy, especially in the exam. Acid ionization constants are given in a table. If you need them, they will be given for sure. Then nobody memorizes any constants. Okay. One more thing about acids. We have a concept check on slide number 15. We have HF, HNO2, acetic acid that we just worked on, and HCN. So Ka values are given, 6.8 times 10 to negative 4. For HNO2 is 4.5 times 10 to negative 4. Acetic acid 1.7 times 10 to negative 5. And for HCN hydrocyanic acid is 4.9 times 10 to negative 10. If we want to rank them based on decreasing their pH, highest pH means least acidic, to the lowest pH. Most acidic. We just need to pay attention to Ka values. The relation between pH and Ka values is this. If you pay attention, this one is the highest Ka value because of the exponent. These two are the highest, and if you compare the numerical part, you see that 6.8 has the highest Ka. So the highest Ka has the lowest pH, means this acid could dissociate more. So you put HF here, the lowest pH. Then which one is acetic acid? HC2H3O2. Then you have wait a minute. No, HNO2. I'm sorry, I made a mistake. HNO2, yeah. First HF, which has the highest Ka. Then the second highest Ka is HNO2. Then the third highest Ka is acetic acid. And the lowest Ka, or the highest pH, belongs to HCN. So there is an inverse relationship between Ka and pH. So the highest the Ka, the lowest the pH. Okay? And the lowest pH means, if you remember, the scale of pH is from 1 to 14. pH lower than 7 is acidic. So by lowest pH means it's more acidic, and makes sense because Ka is higher, means products are higher than that of the reactants, means it was a better acid, it was a stronger acid to change it to more products. And if the pH is higher, means the compound is the pH is more towards basic, and Ka is lower. Now we can do some calculations on Ka. We are working on the pH and Ka and building our ice table. Again, I told you it's a combination of chapters 14 and 15. So let's work on slide number 18. Sore throat medications sometimes contain the weak acid phenol. A 10 molar solution of phenol has a pH of 5.43. Instead of writing the formula for phenol, let's just write down HA. As I told you, it's useful everywhere. And if this is an acid, it's going to donate its proton, so it's going to change to an anion plus hydronyl Y. All right? So now, it says a 0.1 molar solution, 0.10 molar solution, has a pH of 5.43. pH of 5.43. What is the acid ionization constant? We are trying to find Ka. So don't forget, Ka is the same Ka equilibrium that we write for acids. So basically that's the same equilibrium constant, we write it for acids. So let's build our ice table again. At the beginning, nothing, right? And we do not write it for H2O because H2O is a liquid. It eventually does not appear in Ka, right? So what's the point of writing it? C, during the change, something called X will be decreased, will be subtracted from the concentration of HA, and the same amount will be added to A and to our products. Why? Because all of them have a coefficient of 1. And then at the equilibrium, then we will have 0.10 minus X, X, and X. So we are going to find Ka as concentration of A times concentration of hydronium ion divided by concentration of HA. So which is going to be X times X, it's X squared divided by HA is 0.10 minus X. But seems like we have two unknowns, but let's find out how we can work on one of the unknowns, because we need to solve for Ka, so we must have X. In the question it says pH is 5.43. When pH is 5.43, how would you calculate the concentration of H3O from pH? Concentration of H3O is 10 to negative pH, right? Is 10 to negative 5.43. So you will find this concentration as 3.7 times 10 to negative 6. So which is the same as concentration of A also, right? So that's your X, correct? Now just plug it in. Now you have it, and plug it in. So you have Ka is 3.7 times 10 to negative 6 squared. I'm plugging into this equation. Divided by 0.10 minus 3.7 times 10 to negative 6. So Ka is going to be 1.4 times 10 to negative 10, according to what you have on your PowerPoint slide. Okay, so combining and working on the concept of equilibrium, it gives us the Ka. Now, what if, okay, you need, in the second part of this same question, is asking for the degree of ionization. For the degree of ionization. So, part B of this question is asking for degree of, let me call it DOI. Degree of ionization is the part that has ionized. It was X, right? Divided by the initial concentration. So the concentration remaining concentration divided by original concentration. So what was X? 3.7 times 10 to negative 6 divided by 0.10. It's going to be 3.7 times 10 to negative 5. So the remaining concentration at the end, at the equilibrium, divided by original concentration, is going to give you degree of ionization. And if you need the percent ionization, is degree of ionization times 100. So we want to find out what percentage has been ionized. So which is, in this case, is times 100, which is 3.7 times 10 to negative 3. Or if you want to change it to just an ordinary number, it's going to be 123.0037%. Only this much has been ionized. So you see, we're dealing with weak acids. Only this much has been ionized, comparing to a strong acid, which is 100% ionized. Okay, we keep going with these calculations, but we might be able to do some assumptions, to make some assumptions to make the calculations easier. So let's see if we have a, yeah, we have an example here. Working on slide number 23. Let's see what it has for us. Para-hydroxybenzoic acid is used to make certain dyes. What are the concentrations of this acid, of hydronium ion, and of para-hydroxybenzoate ion? So instead of confusing yourself with all of these weird names, which are organic names and you have no clue about organic compounds, let's just work the very same equation I asked you to keep in mind. HA is the weak acid plus water, and that's the equilibrium. It's the anion. This is the peroxybenzoate, perohydroxybenzoate ion. But you don't need to be worried about any formula, anything. Just go with your magic equation. Plus H3O. So the question is saying we have a 0.2 molar of this acid, and we want to find out the concentrations of this acid, hydronium ion, and this anion at equilibrium, and then find out the pH of the solution. So as you pay attention to the PowerPoint slides, it's using the same equation. We're not going to confuse ourselves with the formulas or anything. We don't want to make it difficult for ourselves. So again, build your ice table. Initially there is no product. During the change, the coefficients are 1, so there is an x subtracted and there is an x added to the product. So at the end we have x and x. Ka is given, so let's just write the equation for Ka. Is x squared divided by let me see, what was the value of Ka? 2.6 times 10 to negative 5. So what's the value of, what's the coefficient? 1 and 1 and x, so x squared divided by 0.200 minus x. Oh la la, it looks like a quadratic equation, right? But let's make an assumption first to see if we are able to skip that quadratic equation. What is that? If the original value, original concentration over the Ka is more than 1000, then whenever you have the concentration minus x, you can exclude that x. So you can say 0.200 minus x is almost 0.200. So let's see if this is valid. What was the original concentration? 0.200. What is the Ka? 2.6 times 10 to negative 5. If you do this calculation, this is more than 1000. So go ahead and eliminate that x here. Then you eventually will have 2.6 times 10 to negative 5 is equal to x squared divided by 0.2, and do this calculation and get the square root from x. So x, which is going to be what? The concentration of hydronium ion and the anion are going to be they're going to be 2.3 times 10 to negative 3 molar. Okay? Now you're supposed to find pH. It's easy now. You have the concentration of H3O, so pH is minus log of H3O. You put this in log and you get the minus log. pH is going to be 2.64. So you see, whenever you have this type of calculation, first see if the original concentration of your acid divided by Ka is going to be more than 1000. We have a 0 here missing. If it's going to be more than 1000, then you eliminate x from when you have an addition or subtraction to be able to skip that quadratic equation. If this is not more than 1000, then you will have to unfortunately go with the quadratic equation, which is longer. Not harder, but it is longer. Okay. These equations, the examples we worked on so far were about the monoprotic acid, when your acid just had one ionizable hydrogen or proton. But what if your acid has more than one ionizable proton? What should we do? Ready? Okay. Tartaric acid is a diprotic acid. So again, don't worry about the formula. Instead of HA, and by the way, I'm working on slide number 27. Instead of the formula for tartaric acid, because it's diprotic acid, let's put H2A. So far your acids were monoprotic, so you just had one hydrogen. Now it's diprotic, so we put H2A. And the same thing, the same procedure. You add it to water, we call it hydrolysis, and you have an equilibrium. Now, when your acid has more than one proton, you can take one proton from it at the time. So you cannot eliminate both of the protons at the same time. So you should say it only releases one proton, so it will change to HA plus H3O. Okay? And in the question, the acidic equilibrium constants are given. This is Ka1. It's 9.2 times 10 to negative 4. What are we supposed to find? pH of the solution and the concentration of tartarate anion. So when your acid has more than one acidic hydrogen, you need to remove the hydrogens one by one. So what is this is 0.10 molar. So build ice table for the first ionization. 0, 0, minus X, plus X, plus X. Then at equilibrium you have 0.10 minus X, X, and X. So Ka1 is X squared, and Ka1 is given, let's just plug it in right away, times 10 to negative 4 is X squared. So make that assumption, try that assumption, check it, see if you can eliminate this or not. So original value divided by Ka. If you put it in your calculator, it's going to be more than 1,000, thank God. So go ahead and eliminate that X. So at the end, is it? No, it's not, sorry, my bad. It's not, unfortunately. So I know that you know how to deal with the quadratic equation. You cannot eliminate it. So you do the cross multiplication to build your quadratic equation. X squared, and then now this side is going to be plus 9.2 times 10 to negative 4x and minus 9.2 times 10 to negative 5. Okay? And then now A is 1, B is 9.2 times 10 to negative 4, C is minus 9.2 times 10 to negative 5, and then you know how to find the roots for quadratic equation. Minus B plus minus the square root of B squared minus 4AC divided by 2A. When you find it, it gives you two values for X. One of them is negative, and the negative value for concentration does not have any meaning. So when you find X is going to, I'm not going to work on that. I know how you can work on it. You had it before. So you get X, this amount, and minus 1.0 times 10 to negative 2. All right, so concentration cannot be negative, so you keep the positive one. Now, what was X? X was concentration of H3O and HA. It's a little bit different now because you have more than one step. So it's going to be 9.1 times 10 to negative 3. And the concentration of H2A, sorry, on this side is going to be 0.10 minus 9.1 times 10 to negative 3, which is going to be 9 10 to negative 4 molar. So, are we done? No, because this acid is not going to stop at this point. You cannot hold it and say, hey, do not ionize anymore. You cannot control the acid. It's going to go to the second step to lose one more hydrogen. That's the difference between monatomic and more than monatomic acids. So, allow me to erase my ice table. And I will keep the concentrations though. So, if I want to write the second equation, I prefer to write it in a different colors so you're able to see the difference. What do we have in the second? What is going to hydrolyze more, to lose hydrogen, more hydrogens? This one. HA is your reactant. Pay attention. This is the change that you had so far. Plus H2O. The same thing. The remaining of this acid is going to be HA with a negative charge, which is going through another hydrolysis process. It loses its last hydrogen and it had a negative charge already. When it loses another positive hydrogen, it becomes negative 2 plus H3O. Okay? Now, what was Ka2? That's why you are given two Ka values. You see, in the question you had Ka1 and Ka2. Ka2 is 4.3 times 10 to negative 5. 4.3 times 10 to negative 5. And by the way, you learned something here. When you have more than an monoprotic acid, more than one acidic hydrogen, Ka1 is normally larger than the rest of the Ka values. Means that the fresh acid seems like it's stronger than, by losing hydrogen, it loses its acidic strength. If you can compare the Ka1 and Ka2 to one more decimal. Anyway, let's build the second ice table. Now, what was the value for HA that you found? Now what you found, you put it here. 9.1 times 10 to negative 3. And 8 to negative 2, we don't have it, but you have a value for H3O. That's the first time you have something for a product. What was the value for H3O? That's the same, right? 9.1 times 10 to negative 3 molar. They are all left from the previous step. They're leftovers from previous step. Then now you have minus X, and plus X. So 9.1 times 10 to negative 3 minus X, and then X, and 9.1 times 10 to negative 3 plus X. So if we erase this part, then the shape of Ka2 is a little bit different. Ka2, we said it's 4.3 times 10 to negative 5 is equal to, you have X times 9.1 times 10 to negative 3 plus X, the product of the concentrations of products, divided by concentration of the reactant. 9.1 times 10 to negative 3 minus x. All right. So now if you compare the, if you divide the original value, this, by this value is going to be, again, more than 1,000, then you can eliminate these. And then you will have 9.1 times 10 to negative 3 times x is equal to these two times to each other, and x is going to be 4.3 times 10 to negative 5 molar. Is it? Okay. So, yep. What was x? X was the value of the one that the anion that you were asked for. It was mentioned. It's 4.3 times 10 to negative 5 molar. The value for H3O is going to be 9.1 times 10 to negative 3 plus 4.3 times 10 to negative 5, and which is almost the same. So your assumption was valid. And the same for HA. So from here you can find your pH is negative log of 9.1 times 10 to negative 3, which is 2.04. Unfortunately, I don't have that much space in my board. So that's what you do when you deal with acids, monoprotic and diprotic acids. We normally don't work with the triprotic acids because that's going to be much more calculation, and that's enough. That's the longest that you can get. You will have 2 steps and you apply the same exact procedure on 2 steps. The only thing is that the initial concentration for the second step is going to be the remaining concentration from the last step, the leftover. All right, work on this part, and we will work on base ionization, equilibrium, and the rest of the stuff that we have.